Yeah, so today is lecture number 11. So what we exactly learn in 10 lectures? We learn about frequency response, which is composed of magnitude and phase response. And to predict the stability of any system, we are looking at the phase margin. Phase margin is measured using phase at UGBW, and you are writing the equation, and then you can find out whether the system is stable or unstable. But before this, there is one more measure to find out whether the system is stable or not. You need to check all the roots, means poles and zeros, both has to be on left hand side of the S plane, right? And then you need to check stability using Bode plot. So this is one technique, but there are many techniques through which you can predict the stability. Those techniques are part of control theory course, but we don't use it, so we are not learning that right now. But in control theory, like you are taking control theory. So what is going on in control theory right now? Huh? Sorry?
Right now we are learning about the signal flow graph.
Signal flow graph. Okay, that's good.
Actually, until now we are not in the stability part of all these things. Sir, I told that we will take in the later class.
So you are learning to find out the transfer function
By
using SFG and maybe through
there is a theorem also. I don't remember.
state diagram.
State diagram also. Graph.
Okay. So graph theory is also part of our course. It has to be learned before control theory course, so it will be useful. Next topic is graph theory after this. But let's see how much time this will take, because previous few lectures which were expected to be known to you, so that's why I took just it was revision, right? So one lecture was on initial condition and final condition. Initial condition and final condition, depending on like V0 minus and V0 plus, or I0 minus and I0 plus, can be found out by shorting or open circuit the capacitor and inductors, right? Accordingly, you need to see. So the answer will be uh, for a given network, the answer will be either in terms of resistance or maybe open circuit, right? That is what you are going to see. If it is a circuit which is like this, so what can you tell about this I0 minus and I0 plus in terms of current? So in terms of voltages, both have different thing. Capacitor, in terms of current, it's short, right, at low frequency. So I0 minus and I0 plus you can write down, right now I0 minus, and other side it will be open, so you can write down I0 plus also, right? And that you have to substitute in your differential equation. We are doing everything for solving the differential equations, and we learn following things. We are observing the circuit equations which you have written. If circuit equation has integration, because we want to solve the differential equation which will not have any integration, then you have to substitute one more variable called x of t, and then you can solve the differential equation. If it is not there, if only derivatives are available, if the maximum order of your derivative is 1, then this such system is known as linear. If it is more than that, it's non-linear. For solving such equations, let's assume that you have such kind of equation which we kept for surprise quiz last time, right? So solving such kind of equation, you have to write down the characteristic equation, which is going to give you, in terms of Franklin Coue's book, you can write down in terms of P, h of P is equal to P square plus 3P plus 2 is equal to. So this response is available, so you can find out the roots, which are P plus 2 and P plus 1. For these two roots, you can find out C1 times e raised to minus 2t plus C2 times e raised to minus t, and you can find out C1, C2 in terms of final condition I0 plus, or and you can substitute here, right? The most important part is this extra number 4, which is kind of force response. You may have two kinds of response where input is 0. Those kind of responses we can keep it here, like this is a circuit, and let's assume that there is a current as an input and there is a switch. So at t equal to 0 minus time, the switch is, let's call this switch as phi is open, and at t equal to 0 plus, phi is closed. Such kind of input is known as step input, right? Because at 0 time it was 0, and afterwards for infinite time it's 1. This number is normalized 1, and this input is called step. Other cases, we are also giving, instead of this, we are giving just impulse as an input. So impulse looks like this one, right? Where this time t is very small, maybe tends to 0, right? Other than that, there might be the case that you are giving sine wave over here, right? So in all such cases, you can find out this response, which we are going to call it particular integral pi. What we have found out right now, this is called complete solution CS. So CS plus pi is going to give you the response of your circuit, right? This is what we have learned, and we have only learned about RC, RC in shunt, and RLC in shunt. You can keep RLC in series also, and you can find out, and you can make other combinations also, right? So it was not so much complicated. Maybe I covered more in a single lecture, right? But this was the revision. This is what you need to know, right? If you don't know, like what I can do, I can give an assignment, right, where there will be lots of questions will be there, maybe around 10 questions on just solving such circuits using differential equations, right? Okay, so now there is a next topic, which is the most important part. And if you look at this, what I learned from your previous batches of BTech, look, network analysis, all the fundamental analysis, nodal analysis, you know about mesh analysis, other things are also known to you, right? You know how to solve those circuits, but I'm going to introduce some of the advanced techniques. This will be useful for solving some of the complicated things. This is what I as I told you, like I learned from your previous BTech students who are looking for such kind of techniques. So I covered it in our course, which is not written as part of your course curriculum, but we are learning and we are updating the new things. So it will be a part of your course now, and it will be asked in your examination also, right? So I am following this book. I don't know this book is available or not, but if you want soft copy, I can send you the soft copy, right? Yeah, and I'm teaching word by word from here. When I'm following something, I'm following that word by word. I'm not deviating anything, right? So whatever I'm copying, it's from this book, word by word. Okay. So in network analysis, you know KCL, you know KVL, you know mesh analysis, you know nodal analysis, right? You did all these things, right? Somewhere, or maybe uh, in IC 160, IC 161, or maybe in our course also you are doing it, and you will do it. But if the system is LTI, as I told you, linear time integral time invariant system, the solution may be found by ignoring the initial condition. Look, we are not generally taking the initial condition. Initial condition will be zero. As I told you, like all the, if you look at the name of this book, this is computer method for circuit analysis. So let's assume that you are designing some simulator. So in simulator, generally there are two ways to simulate any circuit. Either you keep some initial condition, or you don't keep it. If you are not giving any solution, any option from beginning, means it will take by default initial condition as zero. So all the capacitors are discharged. There is no current in inductor. Nothing is saved anywhere, right? Everything is at zero, and you're starting from zero, right? So that is what we are going to do now. Now, this is also known to you. This is just repeat what we have learned. The nodal admittance formulation is based on Kirchhoff's current law, which states the algebraic sum of current living at any node is zero. Right? This is already known to us. Very good. Now, by the way, this book is really old, so they don't use I, but they use J as current. Okay, J is current. So wherever you are seeing J in this book, it's equal to current. But generally J is presented for current density. Right? So all old authors, they are using J as current. So in this our presentation, you will find everywhere J is current. So here J1, J2, Jk, and maybe Jn plus 1. So there are so many number of voltages are given, and for that this is a some black box where there is some circuit is kept, and when you are going to solve this, you can write down in terms of matrix equation that will be yv equal to j, where y is equal to admittance, v is voltage, and j is current, right? One more thing which I want to tell you, why these analysis, all the advanced techniques, everything is very much useful for solving any circuit, with one assumption that all the circuit, let's assume that you have seen such kind of circuit, right? Have you seen it or not, right? So this can be modeled as like this. This is VB, this is V emitter, and this is V collector. So if you want to solve transistor, you can solve using this this circuit, which has resistance and dependent voltage sources, dependent current source, sorry. Right? So, like, how to model this, how to do this, we are going to learn it in two-port network. So I thought I'll cover even BJT's two-port network also. So it will be useful for solving amplification and everything. So circuit theory is very much important in terms of all the passive components. We are not learning anything active, because every active thing can also be decomposed to a circuit which is made up of just resistance and capacitance, right? Are you following, or is it difficult? Okay. So this model which I have drawn, it is at low frequency. This model is known as low frequency model. This is not valid for very high frequency, because if there is a frequency, if there is high frequency operation, and if you are saying two dissimilar plates, when I'm saying two dissimilar plates means both the plates will have different voltages. If you are seeing that, it's formation of capacitor, which is parasitic, by the way. So there are three plates I can see directly: base to emitter, base to collector, collector to base, right? And if I want to operate the model at very high frequency or high frequency, I am going to introduce few more capacitors, and you can name them as CBE. Sorry, this is CBC, CBE, and CCE, right? And then you can solve this, right, using what we are learning, known as advanced technique. Through that you can solve even BJT, which will be easier. So this technique is very easy technique which I am going to teach you. So that black box I am talking about, that black box may have BJT, may have MOSFET, or may have any transformer, anything. All will be uh, all will be modeled as passive components, and then we are going to solve them using only one equation, which is called YV is equal to J, where Y is admittance. Okay, when we are going to write the admittance matrix, it will have some n plus 1 cross n plus 1 entries, right? First entry we are going to call it y11, then y12, and it's progressively increasing till n plus 1. And another matrix which is going to be voltage matrix, and other side we will have current matrix. So that's how this will become YV is equal to J. Just these are the notations which are we are defining right now, right? So if we are defining the admittance, Yij times Vj is equal to Ji, where I is going from 1 to n plus 1. Similarly, J is also increasing, and Yij is nothing but Ji by Vj. So I am defining the admittance. Admittance is known to everyone, right? Its unit of admittance is 1 by ohm or mho or Siemens, right? So all terminals except jth ground, we can find out Yij equal to Gi by Vj. Okay. And when you are making all the summation, you can find out the current. So this is already known to us. This is again similar to what we have learned in KCL. Yeah, Aishwarya. Yeah. Okay. So some other dot, right? Okay. Okay. So by looking at this, we can say that J equal to 1 to n plus 1, we can establish all sum of admittances in each column of the matrix, and that will going to be equal to 0. This same following the KCL, because the current which is coming inside and which is going outside, you make it plus and minus, and all will be equal to 0, right? That is the KCL. Same thing is written here, but in a different language, right? So same thing I am talking about. Right? This is a current. So at a particular node, current is, let's call this one as, let's call it, so J1, J2, J3, and all currents at particular node is equal to 0. Same thing is written here. And there is one more thing: as long as grounded reference node is not part of the network. So when we are doing the analysis, which we are showing here, okay, where is that? Here, in the analysis, everything is measured with respect to ground or 0 volt, which will not be part of analysis. When we are going to define all these nodes, we are not going to take care of this node separately. If you remember, if you have done the nodal analysis, if such kind of system is there, how many nodes you are going to take? One or two? Only one, right? This one, not this one. So 0 we are going to avoid it. It's not required because everything is measured with respect to 0 volt. So if that is the case, then all the linear dependence among the rows and columns of Y and determinant of matrix is 0, and such matrix is known as indefinite nodal admittance matrix. Okay, so these are just a definition just to start with. Okay, now look at this thumb rule of analysis, which says there are two sides, one is left hand side and one is right hand side. In left hand side you will have all the passive components through which you are going to find out the current. So passive components through which how much current is flowing you have to write down at the left hand side, and right hand side you have to look at all the independent sources. Not, I'm not talking about dependent sources, I'm talking about independent sources. So all the independent sources uh, in terms of current you need to write down at right hand side, right? Okay, now let's look at the real network. So there is a general node where this is independent current source, right? Others are very simple, and there is a box we are going to call that one is transconductance. It's not resistance, but we are keeping transconductance, right? So can you write down the equation for node I using simple KCL? So still we have not learned the new technique. We are talking about the previous technique only. So I can write down SC times VI minus VJ. Look at the first term, right? The current is this side. Look at the direction of the current. So you are moving from VI minus VJ side. So it will be VI minus VJ times SC. This S is Laplace operator, right? Minus G, because the current is coming inside. Look at the current direction. This is inside. So rate direction is inside, right? This is also inside. So if you're writing this, the next equation is minus G times Vk minus Vi. So it's going from K node to I node, so it's Vk minus Vi. Plus this inductor 1 by SL times Vi minus VL, where this direction is another side. So it's plus and is equal to J, because the current is coming inside, and we are following with the agreement of this equation. We are following this thumb rule because that current source is independent one, so we are going to keep it separate side. You should not be at the left hand side, you should be at right hand side. We are doing this to build up for the admittance matrix. Are you following? Till now everything is KCL, right? Nothing difficult. Okay, if you agree with this, now look at this circuit. All the boxes are actually transconductance, or you can call them as G1, this one is G7, this one is G6. You can call all this as C capacitor C4, C5, and this you can call L3, L2, right? And you are going to follow what exactly you have done previously, and we are not going to include 0 volt, right? So there are 4 nodes. Now let's start with the first node. So somebody can help me to write down the first node. First node. No, J1. Look, we already agree that we are going to keep all the independent sources other side. So right now, do not worry about independent source. Let's talk about G1. What should I write? G1, V1, hmm? Sorry? V1 minus V4. Look at this. This is V4. V4 is not equal to 0. Ground is separate. Ground is not connected here. Look, this this might be the circuit which has lots of transistors. I break them and I made some other circuit. So that's why 0 volt is somewhere else than this 4. In between this, there is a infinite impedance, right? So 4 is not equal to 0, right? V4, then yeah, you write down. If you have not done it, then you have to do it. So this is very important analysis, right? The answer is already available in the next slide. Look, it's not difficult. So how many currents you are seeing? Look, this is one, this is another, right? And when you are doing this analysis, at that time, all other nodes are actually zero, actually. So that's why this is going in different direction or relatively lower than 1. That's why the current travel is from 1 to 4, 1 to 3, 1 to 2. So now can you write down for the next one? Plus, yeah, yes. What you are saying? G7, V1 minus V2 plus SC4, V1 minus V2, sorry, plus 1 by SL, but why SL? Look, when you are talking about this, it's not connected to inductor, right? So you have to just look at the third terminal now, the third node. So how much? What will be the value? Yes or no? If I make any mistake, please let me know, right? And that will be equal to. So look at the current direction, minus plus. So you have to make that. So J1, J4, and J3. So now incoming will be plus J6. Okay. J3 where goes? Okay. J6 only, right? How do I find? Look, as per what KCL says. What KCL says? Which node? How do you, but you told that you people know mass analysis, current analysis, no? This is going on top of this. That, yeah, like that is what I'm writing right now. All these equations are like that, no? Look, we are following only KCL for a given node. For given node, how we are doing this? There are two things: left hand side, right hand side. Right hand side, all the current. If you don't want to do that, you can do this also. J6 is, yeah. This is exactly following what you have learned in your KCL. I made it other side just to make it comfortable so that I can convert it to admittance matrix. So at node 1, all are getting same answer, right? So this is copied from the book. Right? Can we write down node 2? DVH will, Divansu will help us. Tell me. At node 2, so SC4 times V2 minus V1 plus G7 V2 minus V1 SC5 V2 minus V3 plus 1 by SL2 times V2 minus V4 equal to minus J4. Anything left? Hmm? Nothing, right? There is no other. Right? Are you following this? This is very easy thing. Like I want to. So this is an old technique. Still, we have not went to my advanced technique. But anyway, if you don't know, then you should write it. Third node. Write it down for third node. Somebody can volunteer, maybe from back. The last. Yes, yes. You tell me it's very easy, right? Sorry? V3 minus V4 by SL3, okay, plus SC5 V3 minus V2 plus G6 V3 minus V1 is equal to J6. So J6 is coming this side. So should I keep plus or minus? Okay. What about J3? Is there anywhere J2 also? No. No, right? You need to look at this symbol. This is independent current source. For independent voltage source, you need to see such symbol, right? So these are the, right? So assuming that you can write down node 4 also, right? Node 3, node. So I'm showing you direct node 4 also. So you can write down, right? Any problem in node 3, node 4? No problem, then we can go further. Okay.
Are you applying before by external voltage?
Which external voltage?
Before.
V4. V4 is not external. This is a node, right?
Take it at 0 volts voltage. I think
No. 0 is separate, then you know it's, look, this circuit is, both the circuits are different. Both the circuits are different.
we see voltage difference, not voltage value at any node.
Look, right now it's V4 with respect to ground. Ground is different value.
So I think that if you take equal is 0, then answer will be the same. Of current, I'm talking about current, not
No, no.
voltage.
Right now, look, V4 I have not kept anywhere 0. In between V4 and like this node and this node, there might be something else which I am not showing right now. In between this, there might be some transistor. It's not same, by the way. Okay, for your information, it's not same. You know, the another side of current or another side of voltage, if I am marking as minus, does not mean that this is equal to 0. Okay, right? So you should not follow that. If you have kept that image in your mind that other side is always 0, then it's wrong. Okay, do not do that. Your answer will be wrong. Okay.
Sir,
Hmm.
how do you decide which junctions are to be made the nodes?
Okay, so junction. Let's make some circuit randomly. I don't know. Yes, he likes 0, so I'm keeping 0. So this is V out, and let's make this way only. Okay. So how many junctions do you see here? Let him try. Okay. Or if you like, let's say I'm keeping this. So look, you need to look at the junction. Yes. So there are 3 junctions. In total, there are 3 junctions: 1, 2, and 3. But as we agree at the beginning, 0 we are going to drop it. We are not going to take 0. But if this is not the case, if this is the case which we have made it just now, then this will be third node also, right? Okay, so you can write down this equation and you can solve it, right? You done it somewhere. You can solve it. We are not going to solve it right now, but what I want to teach you is, if you want to analyze such network using KCL or KVL, means plain KCL or KVL, will take little bit time. I am going to teach you another technique which is known as admittance matrix method. What it says, I want to teach you something called admittance matrix method. Directly you are going to have yv equal to j. So y is readily available. Means you need to be little bit sharp. By looking at circuit, you can give the uh, you can look at the current and voltages. So first of all, you need to identify the voltages or the nodes. You can do that for any circuit. You can find out how many nodes are required, like 1, 2, 3, sometimes 20, sometimes hundreds, right? So if you can find out how many number of nodes are available in the loop, what you can do, you can write down a matrix. Let's assume that we are going to write it for this guy, whatever the circuit is given. We are going to write a matrix which are going to have three different nodes, v1, v2, v3. Let's call them 1, 2, 3. You mark them here. Sometimes this is easy way. Just if you are starting first time, it's easy way. But before going to that, or before becoming expert of that, this is a admittance matrix derived from what you have found out in the equations. Whatever four equations we found out, this has written in terms of yv equal to j. And there are some certain observations you need to see. Those observations says that if you are looking at the matrix diagonal entries, all diagonal entries are positive and rest of all entries are negative. Can you see, right? This is a like observation, and this says that all these numbers are like, this is y11, like I'm writing diagonal entries, this is y22, this is y33, and this is y44. Do you agree with me? When we are doing this, it means that how much admittance is available on the path when there is only one node is available, which is 1, and I am measuring everything with respect to 1 only, means other nodes are 0. I am not going to look at other nodes are 0. Means when I am looking at this node, if I am making other nodes 0 and then enter the enter all the admittance entries, that will give me y11. If I am looking at y22, then I need to make other node 0 and I should look at all the admittances. And when I am doing this, all admittances has to be in positive. They cannot be in negative. Now let's do that in that case. So if I am looking at V1, other nodes are 0. So you can keep 0 in your mind. So here I can see 1, 2, 3 and 4 passive components, right? Which are connected to V1 node. All have to be in positive, positive sign and they have to be written here in the form of admittance whose unit is more, right? Means if I am want to write down here in this path, I am seeing 1 by r1, not r1, because I am entering something for the unit of mho, right? Next one is capacitor. This is SC. Inductor 1 by SL1, right? Are you seeing anything else? Okay, one resistance is also left, right? We can write down this, there is no problem. Now let's go diagonally here and look at the second entry, which is y22. Y22 is the one when others are 0 but 2 is positive, others are 0. So somebody can help me to write down this. Yeah, SC plus 1 by R3, right? Similarly, somebody can help me in Y33. 1 by R3 plus 1 by SL1, 1 by R2, right? Okay. Similar thing you have to follow for other part also. But when you are doing this, you have to make sure that all these entries are negative. When you are applying same theory here, you have to make sure that all these entries are negative. Now let's follow that and let's write down that matrix too. So this will be y21, y21. So okay, sorry, y12. So I am traveling from 1 to 2. Earlier I was looking at all other nodes also. When it was y11, I was looking at second node, third node, all other nodes I was looking. But when I am looking for y12, I am only specifically looking for the passive components which are available between 1 and 2 node, which will be negative. So what is between 1 and 2? Only capacitor. So I will write down SC, but it will be with negative sign. Direct connection. Direct connection. Okay. And still our theory works where you might have such kind of thing. Then you have to keep that right hand side. Okay. We are going to look at just admittances. Right? Can we write down this third part? Y13. Hmm? Minus 1 by SL1 minus 1 by R2, right? Similarly, can we write down Y21, Y21? Hmm? Minus? Yeah, maybe. Right? So you can make all these observations, no problem. So tell me here, what is going to be here? That's it, right? Okay. So you are saying that it's same as what you are seeing there, huh? Right? It's same, correct. You are right. Okay, so if you agree with this and if you are expert of this, let's look at the node. Okay, let's go to the first one where it was clean one. Okay, now we are going to write down the admittance matrix. So I am not talking about how to solve and how to find out the transfer function, right? That will be found out by your matrix algebra, Cramer's rule, all these things, right? In future we are going to use it. Just become let's become expert of writing admittance matrix. So how many nodes are there? So there are 4 nodes. You can write down 1, 2, 3 and 4. Here also 1, 2, 3 and 4. Hmm.
give the admittance matrix, you told that there will be n plus 1 row and n plus 1 column.
Hmm. N plus 1 is equal to total number of nodes. That was defined by book, right? So where is it now? Right? So if there are 4 nodes, 4. There are 4, right? So 1 to 1. Now, can you tell me what will be the entry? 1 to 1. So, G1 plus G7 plus SC4. Done. Okay. So what about the second? Y12? Hmm? Minus SC4 minus G7, right? Done. Y13, 4, 1 4,
Minus G1.
right? So similarly, you can feed all other entries. I didn't had my lunch, so I need to go now. Yeah. So you can see these entries, right? Must be matching with what we have done. So you can see that, right? It's matching. So you can look at we are going to look at different networks, and we are going to introduce somewhere transistors also, so that you can solve those transistors and you can find out the admittance matrix. For few days we are going to do just admittance matrix, and then we will go to impedance matrix, and after completing this we will go to how to derive the transfer function. That will be the next part, right? Is it easy or difficult? Yeah. So through this you can find out any circuit's transfer function or its response. And once you have the transfer function, which will be, look, there are 4 cross 4, so the order will be most likely s raised to 4, right? So through matrix manipulation you can find out all those things.